A review of chapter 6. So if you want to solve this, first you would need to get the sine theta by itself and then get your reference angle. Find our reference angle by doing sine inverse of the positive. Then with your CAST rule, sine is negative in quadrants 3 and quadrants 4. So then our answers would be 3.87 and 5.55. And I really should have 3 decimal places, not 2, but that's all I wrote down when I did it first. Second one, same thing. First, you get tan by itself and find your reference angle. Again, make sure you do tan inverse of the positive number. Then tan is negative in quadrants 2 and quadrants 4. So you would get our answers, 2.78 and 5.92. To the non-calculator ones. Our first non-calculator one, when you get cos by itself, you get cos theta equals 4, which is not on your pie plate. But since it's bigger than 1, it's not possible. So we have to be aware that if you get sine theta or cos theta and get a number bigger than 1, you can't draw that triangle. Because as a fraction, that would be 4 over 1, and that's your hypotenuse is 1, and your side length is 4. That is never possible. And the second one, this is what's going to be new in chapter 7. In chapter 6, they always gave you a domain, solve between 0 and 2 pi. Or sometimes it was negative 2 pi and 2 pi. And they could change it pi over 2 to 3 pi over 2. In chapter 7, they say solve it for everything. So what does that look like? Well, you start by solving it just like you would between 0 and 2 pi. I get tan by itself. I get 1 over root 3, which you might recognize is the same as root 3 over 3. That's on your pie plate. So we find the pi over 6 family in quadrant 2 and quadrant 4. This would be solving between 0 and 2 pi. Now, when you have to solve forever, does it make sense that one of the answers, which is 5 pi over 6 right here, if you kept going, you'd get coterminal with it again if you added 2 pi. And then coterminal again if you added 2 pi again. So every time we add 360 degrees or add 2 pi, we get another answer that would work. Do you remember in chapter 6 having to write all the coterminal angles with something? Where you had to add 360 degrees times k or 2 pi times k if it was in radians, where k was an integer. So that idea of writing all the coterminal angles and the idea of solving gets put together, and in chapter 7, we'll start writing answers like this. You take the two answers you found from 0 to 2 pi, which is 5 pi over 6 and 11 pi over 6, and then you write all the coterminal angles with them. So we write 2 pi times k, and I don't know who decided this, but they're like, wouldn't the k be the nicest if it was in the middle? Kind of makes more sense to do 2 pi by itself and then k at the end, because you're doing 2 pi as many times as you wanted, but for whatever reason, the k got put in the middle.
Does it have to be put in the middle?
No, if you write 2 pi k, that's fine. If you want to write k 2 pi, that would be fine. Now I've got a visual of 5 pi over 6, which is here, and 11 pi over 6, which is down here. They're both part of the pi over 6 family, so that would make a straight line all the way through, cutting your circle in half. Okay? The idea with this is you would take 5 pi over 6, and every time you go around the circle again, you would be coterminal, and that would be another solution. However, sometimes in multiple choice, this same answer gets written like this. And what they're saying with just the k pi, that's just going halfway around. You see with this going halfway around would end here. And then halfway would get to this one again. And then halfway to this one. And this answer is considered a little bit more elegant because it's shorter. But you can only write it shorter with tangent. Because tangent's the only one where it's both positive and negative right opposite each other. Sine and cosine, you would have to still answer it like this. This is giving you a taste of what's called the general solution. And we want to write down the steps for the general solution at the top of page 574. These are the basic steps for writing the general solution. You redo chapter 6. You solve like normal from 0 to 2 pi. Then to every answer that you get, you're just going to add 2k pi. And that's new idea number 1 for chapter 7, which just combines 2 ideas from chapter 6 together. So that's why it's a really good review for chapter 6. On your chapter 6 test, you won't get any general solution questions, but you will get solve between 0 and 2 pi questions, and you will get can you write all the angles coterminal with questions. Just not combined in the same question. So then on page 574, you have example 1. You can put a line through that one, because we're going to do this question, or we're going to do 3 little questions instead. Here's the first question. And the only thing different from chapter 6 is now we have this part right here, which tells us it's the general solution. We have to write all of the answers. So to begin with, we get sine theta by itself, which is negative 1/7. And then we find our reference angle. Which is a terribly fascinating result, because the reference angle is 0.143, rounded to 3 decimal places. And 1/7, my favorite fraction, by the way, is 1/7, is also 0.143, rounded to 3 decimal places. But they're not exactly the same. Like, if I go 1 divided by 7, I get 0.142857. If I do sine inverse of 1 divided by 7, I get 0.1433. Very close, but not the same. If you take AP Calculus next year, you're going to find out why this happens. And this is true for any small number and sign. If I take another small number, like 1/10, that one you can do easily in your head, right? Mm-hmm. So I won't even push enter. I'm going to trust you can do that in your head. And I'm going to go show you what sine inverse of 1/10 is. Pretty close to 1/10. Question?
Is there any number where, any fraction where the sign of it is the same as just its normal?
Like perfectly the same?
Yeah.
0. Sine of 0 is 0. Yep. And 0 happens to be 0.
Yeah.
But all the other ones get really close. Like, in fact, if you do 1 253rd, and then I go sine inverse of 1 divided by 253, Look how close they are. The closer you get to 0, the closer they match up. When you take AP Calculus, you'll be able to figure out why this happens with something called linear approximation. So you'll have to wait till next year to find out. But it only happens with sine, not with cosine, not with tangent. So it's interesting that way. And then, I think we have time. I'll explain why 1/7 is my favorite fraction in a second. But once you've got your reference angle, then you can solve, because it's going to be in quadrant 3 and quadrant 4, what your angles are. And once you have your angles between 0 and 2 pi, this is just like chapter 6. The only thing new now is we add 2k pi to each of them to make the general solution. All right, so a little bit about 1/7. Why do I like 1/7 so much? Well, first of all, I like knowing my fractions to decimals. I find it useful for mental math. So I know, for example, 1/2 is 0.5. Well, you guys know that too,
Very impressive.
right? And 1/3, it's cool because it's 0.3 repeated. And a quarter is the same value as a quarter, 0.25, 25 cents. And a fifth's not hard. A sixth, a little bit weird. Half of a third, which is 0.3 repeated, is 1.6 repeated. But my favorite is 1/7. Because 1/7 is 0.142857 repeated.
Oh.
Whoa, it's already pretty crazy that way. And it's actually pretty easy to remember, because if you double 7, you get 14. And if you double 14, you get 28. And if you double 28 and make a small mistake, you get 57. It's really cool that way. But what's also really cool about sevenths is you can do any seventh and see if you can see the pattern. 2/7 happens to be 0.285714 repeated.
I think I'm seeing that pattern.
3/7 happens to be 0.428571 repeated. I'm going to skip a few. Now, what do you think 6/7 is? You thought I'd skip to 7/7 and be all impressed with yourselves. Yes. 0.857142 repeated. You notice it's the same numbers in the same order repeated every single time? Just, you start with the smallest number, and then the second one, well, what's the second smallest number in here? The 2. So you got 285,714. Then the third smallest number is the 4. 428,571. The biggest number is going to be the 8. 0.857142. I don't know. I just think that is super cool. And it's like 6 decimal places repeated. That's like, you get to 1/8. 1/8 is boring. 1/9 is pretty cool. I can't get too off topic though.
You don't want to go on a tangent about fraction.
Yeah, I don't want to talk about weird numbers like 0.9 repeated.
I know that you do, but you just don't.
I know. We'll see. If we have time at the very end of class, I will talk to you about 0.9 repeated.
We're going to have 0.9 repeated is equal to 1.
Mm-hmm.
When you went over this last
I might have. So much fun. And then the 11ths are super cool. Like 1/11 is 0.09 repeated. Super cool. 12ths are kind of boring, but kind of neat. 13ths. They must be cool for some reason. Maybe they're unlucky. This would be a calculator question, yes. I'd like you to try this one on your own. I'll put up the answers in a bit. There is our answer. I know. I was on a 2 decimal places mode when I did these notes. So. And finally, this is a good review one from chapter 6. We have to solve for theta. We have a tan squared. So then we'd have to either factor or use the quadratic formula. Does this one factor nicely? No. So we have to go to our formula sheet. And on your formula sheet it says for ax squared plus bx plus c, wow, equals 0, that x is equal to negative b plus or minus b squared minus 4ac over 2a. And if you don't have it memorized yet, start memorizing it, because you don't get a formula sheet in AP Calculus next year, or currently. You don't get a formula sheet in AP Calculus.
No, you can use.
So you have to know formulas like this. Now, this is for ax squared. We have a tan squared, so instead of x equals, we will have tan theta equals negative 3 plus or minus 3 squared will be 9 minus 4a is 1, b is negative 7 over 2 times 1. And if I simplify this, I get negative 3 plus or minus negative 37 over 2, which means we'd have to split this up, because this is actually 2 different answers. One answer with the plus, and one answer with the minus. I hope you can see that those are not on your unit circle. But just because the numbers are a little bit ugly looking, doesn't mean it's any more difficult than what you did before. How do you solve? You need to find a reference angle. Maybe temporarily you want to type these into your calculator just to see, are they positive or are they negative? But sometimes fractions like this is not easy to tell. Okay? So I type into my calculator negative 3 plus the square root of 37, all divided by 2, I get 1.541. And if I do the same thing with the other one, and some calculator tricks, you know, you can just highlight what you typed in before, push enter, and then if you go in there, all you have to do is go to that plus sign and override it with the negative sign, or subtract sign. Negative 4.541. Next, we're going to need to find our reference angle. So for the first one, again, I can just go up and either highlight that number or highlight the fraction. And I find my reference angle is 0.995. And because tan is positive, one answer will be 0.995, and the other answer will be in quadrant 3, so I would have to go pi plus my answer, and I get 4.137. Second one, we need to find a reference angle of the second one. So again, I'm going to go tan inverse. I'm going to go select the number, but what's the problem if I push enter now? It's negative. So you have two options. You either can cursor all the way back to the negative and delete it, or you can be like sneaky and just say, if I times by -1, that'll also change it to positive. And I get a reference angle of 1.354. In this one, we need to find theta in quadrant 2 and quadrant 4. So we're going to have to use our reference angle twice. Another trick, I've shown you this before, but another trick on your graphing calculator is above your on button is a store button. You can store your answer as any letter you want. I like to use X because I don't have to push an extra button. If I store it as X, I can now go pi minus my reference angle for quadrant 2, enter, 1.788. And in quadrant 4, that's going to be 2 pi minus my reference angle. And so it's just quick that I can just go 2 pi minus x, then get 4.929. And all of this up till now is a chapter 6 question. We just solved this between 0 and 2 pi. If you look at the original question, and they did this once on the exam, and now they don't do this anymore. But if you look at this original question, it just says solve for theta. Two things seem to be missing. They don't say anything about the domain. Okay? Usually they'll say either find the general solution, or they'll say between 0 and 2 pi, or they'll say theta belongs to the real numbers. They'll usually say that. In fact, they will now. But if nothing is said, and you're asked to solve something, do you think they want just one answer? Or do you think they want all the answers? They probably want all the answers. So, if nothing is said, it is a general solution question. And if nothing is said, technically radians and degrees would both be accepted, but as we're getting into higher level math, then they're going to expect radians. Because everything you do in calculus with derivatives is all based on radians, not on degrees. So as a general solution, the last thing we would need to do is take all of our answers between 0 and 2 pi. And it doesn't matter the order, but I like to write them in numerical order. And add 2k pi to each of them.
Gracie Johnson to the office, please. Gracie Johnson to the office.
Where k is an integer. You can circle questions 5, 6, and 9.